We're going to look at some of the important processes. There's a process of synchronization, and there's also a process by which important cell parameters are obtained. There's a procedure called random access procedure, which is very similar to previous random access procedures we have seen in 2G and 3G technologies. And then there's something called an attach process. And immediately after the attach process, a bearer is set up, and the bearer enables communication, and each bearer has associated with it some quality of service. So we're going to have a look at the different quality of services associated with LTE, and then we're going to see how data is transmitted on the downlink and uplink, and how mobiles are continuously taking measurements. And last, we're going to look at HARQ. So we start off with radio resource RRC connection scenarios. Now, in these slides, what I've done is I've added a few things. So usually, whatever you see in blue, when a mobile is switched on, a number of things take place before it can start transmitting data. The first thing it does is it scans the frequency bands, and after scanning, it has to synchronize both in time and frequency, and this happens in other technologies as well, both in 3G as well as in 4G. A mobile has to first synchronize in both the frequency space as well as in the time space, and thereafter it starts obtaining parameters that the cell is broadcasting on the downlink, and that information enables it to know something about what sort of bandwidth is being used in the cell and other important information. And once it has obtained all that information, it can initiate an RRC connection. Okay, and an RRC connection enables it to get a signaling bearer, and once it obtains a signaling bearer, it can do a network attach. And when it does a network attach, it connects to the gateway. So you can see the first four processes: scanning, synchronization, obtaining downlink parameters, RRC connection. All of these processes take place between the UE and the E node B. However, the last process, the initial network attach, that process takes place between the UE and the gateway. Okay. So in terms of, I've used the word bearers. So there are two types of bearers that you can have. You have something called user plane radio bearers. These bearers carry user data, and then there are signaling bearers that carry signaling information. So we talked about the difference between user plane and control plane or signaling plane last week. So those two pieces of information are handled separately. In terms of signaling, in UMTS we saw there were 5 types of bearers that we could have for signaling, whereas in LTE they've simplified it, and there are only 3 types of bearers that you can have, and we'll discuss them in the next slide. Okay. Now we've seen this diagram describes the endpoints and the intermediate nodes in a communication. So at the end of the day, a UE is communicating with some peer entity. Peer entity could be a server, or the peer entity could be a person, and you have some end-to-end service established between the UE and the peer entity. Now, in order for this communication to take place, we have to have initially we have to have a signaling radio bearer set up, or SRB. So an SRB is essentially a radio bearer that only carries signaling information, and there are 3 main types of SRBs. So the first type of bearer is a bearer that is first set up. Obviously, before the first type of signaling always takes place in the common channel signaling. So you have SRB0, which is set up for all RRC message associated with common channel signaling. Then a second bearer called SRB number 1 is set up, and this is set up for all RRC signaling. And if there is no SRB2, then you would use SRB1 for your NAS messages as well. The third type of bearer is called SRB2, and SRB2 carries NAS signaling. That's the network associated signaling between the core network and the user equipment. So we have different terms: radio bearer, S1 bearer, S5, S8 bearer, and all of these put together are referred to as the EPS bearer. Okay, so if you look at it, what are the things that have to take place when we do an attach? Okay, when we do an attach, we have to select an MME, because remember, all network related signaling has to be done with the MME. And once we select an MME, the user has to be authenticated. And once the user is authenticated, the user is allocated an IP address. And once the user is allocated an IP address, you select the serving gateway and the PDN gateway. And thereafter, all the bearers are established: the S1 U bearer, the S5 S8 bearer, and so forth. And now the RRC has to be reconfigured to allow user data traffic. So there are two processes associated with the RRC connection setup. The first step is a contention-based process, random access process, just like in GSM and in 3G. The initial RRC, the initial random access connection is a contention-based process, because a number of stations could transmit a random access message at the same time, resulting in collision. Okay, but if that random access does get successfully through the network, then a connection can be established, and the user can then have a data connection. So initially, when a user is requesting a connection, it has no dedicated resources allocated to it, so it can signal to the node B. Okay, so the only channel it can use is the uplink common channel. Okay, and it's very similar to the RACH that we had in GSM. Okay, and it's possible that there could be collisions when two UEs try to use the same RACH channel. So let's move on. We're going to look at synchronization, because remember, the first process that takes place, what happens in synchronization? Well, when you switch on a mobile has information stored in it. It has information stored in its SIM, and it has some information stored in its mobile equipment as well. Most of the information that's stored in the SIM refers to the preferred PLMN that should be used, and the carriers, and also the ME will have information about the category and the capability of the equipment, because some equipments are capable of MIMO, others are not capable of MIMO. So when you switch on your mobile collects all that information, and it knows. Then what it does is it starts synchronization. Okay, so there are two, in terms of synchronization, three important things that need to take place. One is referred to as slot synchronization, and this is where you need to be able to sort of know where symbols start and where symbols end, so that you can count your symbols and so forth. The next thing is frame synchronization. Once you know where symbols start and symbols end, the next thing you need to know is where does the frame start and where does the frame end. Okay, and we need to pick up all this information. And then the next thing that you have to do, once you know where the frames start and frames end, then you start looking for certain information related to cell parameters, which are broadcast. Okay, these processes are very similar to the process that take place in UMTS as well. Get information from the cell. Now, in order to perform this, it uses 3 important channels. So the first channel is the primary synchronization channel, and the second channel is the secondary synchronization channel, and the third channel is the BCH, the broadcast channel, which contains cell parameters. Okay, I've just brought it forward because it was not the best order. Okay, so this information, the primary synchronization, the secondary synchronization, and the broadcast channel are all transmitted on the 6 centermost resource blocks, whatever the bandwidth. Okay, so whether your bandwidth is 1.4 megahertz or 20 megahertz, the 6 centermost resource blocks are the ones on which you transmit these synchronization information, because it is very easy for the UE to lock on to the centermost frequency, because there's a pilot that is transmitted at the center of the bandwidth. Okay, remember, so it can lock on to that pilot, and then it goes 6 resource, it goes sort of 3 resource blocks this way, 3 resource blocks this way, that gives it 6 resource blocks. It starts looking for information inside there, because this is where the all this information, primary synchronization, secondary synchronization, and BCH are transmitted. So it's essentially 72. This information is transmitted in 72 subcarriers, but not in every time slot. Okay, and we'll see in which time slots they are transmitted. Now, each cell has a number. Okay, just like in GSM as well as in 3G, we allocate certain number to a cell, and this number is referred to as a physical cell ID or PCI. And the cell ID information is very useful for the UE. Okay, now how do we work out the cell ID? The cell ID is made up of 2 parts. There is a group ID, okay, and there is a ID within the group. So generally for the cell ID, for the group ID can take numbers between 0 and 167, but for the ID it takes only 0, 1, 2. Where do these numbers 0, 1, 2 come from? Well, remember, if you have a 3-sector cell site, each one of these sectors will have either 0, 1, or 2 as its cell ID within the group, whereas all of the 3 cells together will have the same cell group ID. Now that's very important, because a lot of times you want to know if sometimes when you're performing handovers, whether you're handing over from one site to another site. Okay, so all of these 3 cells here will all have the same cell group ID, but their ID within the group will be different. Okay, so there are 2 examples given there showing how the cell IDs are worked out. Now, the next thing is, where exactly do we transmit the primary synchronization signal? So the primary synchronization channel, we said earlier, is used for slot synchronization. So the primary, as says here, primary synchronization channel we transmit it on certain positions. We transmit it on the last OFDM symbol of slots 0 and 10 in the first and 6th subframes. So this is your first subframe, this is your 6th subframe. So in the slot 0, so within the subframe there is slot 0. Subframes will go from subframe 0 to subframe 9 because there are 10 subframes, and slots will go from slot 0 to slot 19. Okay, so essentially in slot 0 and slot 10, in the last symbol, it's transmitted on the last symbol. Okay, so this is the position. Okay, so remember, within each slot, if you're using, for example, if you're using normal CIP, you will have, how many symbols will you have? 7, so it will be on the 7th one. Okay, are you guys okay with that? Now look at the diagram for the downlink. One good thing about studying these 4G technologies is this diagram here, this slide, the figure 6.10 shows 5 megahertz bandwidth. So in 5 megahertz bandwidth we have 25 resource blocks. Okay, that's vertically, or on the y-axis you can see 25 resource blocks, and on the x-axis you have slots. So slots going from 0 to 19, so there are 20 slots, so that corresponds to one frame. Okay, now first thing I told you was a primary synchronization channel. Okay, now I told you that this is transmitted on the center resource blocks. Okay, so because there are 24 resource blocks, the center resource blocks are approximately between 11 and 15. Okay, more like, so more like between 10 and a half and 16 and a half. So here, this, you see this position here, if you look at the last slide which we talked about, it said it's on the last symbol of slot 0 and slot 10. Okay, so this is where the primary synchronization information is transmitted, the parts that I've shown in red here. Okay, so it's the ones with the lines, the vertical lines going downwards. Okay, that represents the resource blocks on which we transmit the primary synchronization channel. Okay, so we don't transmit it on every resource block, it's only on the centermost ones, and it's not transmitted on every symbol, it's only transmitted on the last symbol of the 0th and the 10th slot. Now we move on. So first thing the UE will do is it will lock into it will first find the DC subcarrier, and once it finds the DC subcarrier, it will look for 3 resource blocks this way, 3 resource blocks that way, and it will start looking for the primary synchronization channel. And once it finds that, it will do slot synchronization, and then the next thing it will do is try to look for the secondary synchronization channel. And once you identify 2 secondary channels, then you approximately have some kind of frame synchronization. Okay, and again, this frame synchronization has also got very specific positions. So usually the frame, the secondary synchronization is transmitted before the primary synchronization channel, which is up in these positions here. So once you got your primary and secondary synchronization channels sorted out, okay, this is again similar diagram but turned around the other way. The next thing that we look for is this broadcast channel. which is called PBCH. Okay, and the broadcast channel is the one that contains cell related parameters. Okay, now there's a whole bunch of, now there are bits, like some bits like this I've written here, not examinable. I don't expect you to be able to know what's in MIB1, MIB, SIB1, SIB2 and so forth. Because when we broadcast information, we have to broadcast different types of information. So information which I classify as not examinable, I don't expect you to know that. Okay, but the most important thing to know is that there are two types of information that is broadcast. The first information that is broadcast is called MIB, or Master Information Block. Master Information Block broadcast contains things like frame number, what is the downlink system bandwidth. So remember, you can do all of these operations without knowing the bandwidth. Up to now, the UE does not know the bandwidth. Okay, because all it has done is locked onto the DC subcarrier and gone 3 resource blocks on either side and synchronized. It's only once it reads the broadcast channel information, it knows what bandwidth is being used in that particular cell. And it also knows if you're using MIMO, how many transmit antennas are being used, and some other information. And there's a whole lot of other information that is transmitted on the broadcast channel, which enables the UE to work with the network. And as I said again, I don't expect you to know what's in SIB1, what's in SIB2 and so forth. So you can download this book. If you're interested in more information about what's transmitted in the broadcast channels, you can have a look at that. Okay, remember, we also have to broadcast information about handovers to UMTS or GSM or CDMA 2000 network. Whole lot of things have to be broadcast so that once you go outside the coverage area of the LTE network, you can perform a handover. Okay, now this broadcast information, remember last week we looked at all the possible channels. Now this diagram here, if you look at it, you can see that the broadcast channel information can either be transmitted on the PDCCH channel, downlink shared channel, and physical broadcast channel. Right. By the way, this slide is from your last week's lecture. Okay, so I've just put it in here so you can make a correlation between what you're covering this week and what you covered last week. Okay, so this is where the broadcast channel is sitting now. My red is not exactly accurate. Okay, again, you can see that in the diagram I've given you. Okay, so that is the that's where the broadcast information is, and once a UE reads that, it knows the bandwidth that's being used in that particular cell. Now there are also these dots here, these very dark dots. What do they represent? They reference signal. Okay, RS represents reference signal. Okay, these signals are the ones that you measure. So they're reference signals that are used by the UE for taking measurements to assess the quality of the channel. So UE might make measurements on all these reference signals. We'll talk about this reference signal later when we talk about measurements. The steps involved in the cell acquisition procedure are primary synchronization channel, secondary synchronization channel. Then you read the information from the broadcast channel. Okay, you can start reception of the reference signals, and the next thing that you look for is for a channel called PCFICH. Okay, and we'll have a look at that a little bit later. We've now got to the position where your mobile has switched on and it has read all the information, it has synchronized and it has read all the information. The next thing that the mobile wants to do is it wants to initiate a procedure called random access procedure. So what's random access? Again, the word random access should not be new to you. You would have seen that before in both 3G as well as in 2G. So a UE has to request an RRC connection, and when you do an RRC connection, you move from an idle or null state to an RRC connected state. And when do you do this? Well, when you switch on your mobile is in RRC idle, you might want to move to RRC connected. When you do a handover, you will have to do an RRC connection process and so forth. And sometimes mobile can lose synchronization with the base station, and even then it has to perform an RRC connection request. Now we discussed this. This is again something that we discussed a little bit last week, the difference between RRC idle and RRC connected states. Again, take a note of this. It's on page 42 from the Cox textbook, but it was also covered in our slides that we looked at last week. Well, the main difference between idle and connected state is that the UE is on standby. There are no S1 or radio bearers. There's no serving E node B and so forth. Whereas when you are in the connected state, bearers exist. Okay, let's look at the random access procedure. Well, what happens in the random access procedure? Initially, in the random access, you send something called a preamble, and this is sent on the RATCH, and in response to that you get a response again on the PDCCH physical, and when you receive that response, you also get something called a cell radio network temporary identifier. Okay, so you get a number to identify you on that at that cell level. Then you may send a request for transmission on the uplink shared channel, and which will contain your RRC connection requests, and then you will get a response saying that your everything is resolved and your transmission has been received. Okay, and so this is all done. This is the random access procedure. You can think of it as a four-way procedure to get your mobile connected. Now, where is this information sent? Okay, this preamble that is sent by the UE to the E node B is again transmitted on 6 resource blocks that are reserved for the RATCH. Okay, so we have the physical random access channel. Okay, previously P used to use in 3G the word P used to stand for packet, whereas in 4G the letter P stands for physical. Okay, so we have 6 resource blocks that are allocated for the RATCH, and these 6 can be anywhere in the spectrum. It's not like the primary synchronization, secondary synchronization, and the broadcast channel, which are in the center most part of the spectrum. These 6 resource blocks can be anywhere in the spectrum, and they are identified in the broadcast information. And there is a special, somebody probably did their PhD in determining what is the best preamble to use, and this person came up with an with a sequence which is called Z of Chu sequence. So the preamble, this particular preamble sequence was developed by this team of Zarov and Chu, and they developed 64 possible preamble sequences that were available for sale. So you can see that things are getting a little bit more complicated. Okay, you can see that previously the random access messages that we used to send were very simple messages, but right now even the preamble that we use in the random access is from 64 possible preamble sequences. So the E node B has to be able to distinguish which one of the sequences was used by this particular UE. Okay, again, can you make a note of this? This is from page 152 of the Cox textbook, and it shows one possible location of the PRATs. So again, as I said, 6 resource blocks that can be anywhere, not necessarily in the center. So when the preamble is received at the E node B, the E node B sends a response, and it sends a response to the preamble, and it also gives it some timing alignment information. Again, remember, timing alignment was something that we used in GSM and GPRS. We didn't use in 3G, and back in 4G, we start using timing alignment for this purpose. Okay, and the response says, okay, how much should you advance or delay your timing alignment so that the information arrives at the correct time at the E node B. And it also allocates some uplink resources. Remember, if the UE is going to transmit its RRC connection request, it needs to be allocated some resources to do that. So it allocates those resources. Now, the next thing that happens is the RRC connection establishment. Okay, so here the UE now has the resources, so it can send an RRC connection request. This is the point at which it will send its ID, and the ID could be a TIMSI or something like IMSI if you're transmitting it for the first time, or it could be a TIMSI. And in response to the RRC connection request, the UE will again assign more radio resources to establish this signaling SRB1. Remember, all of this signaling so far has been done on SRB0. Okay, so this is the point at which we are establishing SRB1, which enables communication between the RRC layer and the UE. And once that is finished, it has an SRB, so now it can perform an attach. Okay, so remember, after you set up an RRC, that's when you start doing an attach process. Okay, an attach process is where you're going to go beyond the E node B to communicate with the network. So this is where the attach process comes in. So the attach aims at establishing an EPS bearer for user data. So we have something called a default EPS bearer. So whenever you perform an attach, you get something called a default bearer, and then you could be allocated a dedicated bearer. Okay, so there are two terms here, default bearer and dedicated bearer, and we'll come across these two terms a little bit later. So so the attach aims at setting up a default bearer, and in the process of setting up this bearer, this is when authentication takes place, and you get allocation of IP address, and you have an establishment of a radio bearer, an S1 bearer, and an S5 bearer, which are all needed for data and signaling purposes. Okay, so at the end of this attach process, we have a bearer that is set up, And we now go into the next part. So that's the bearer management. So how are we doing? Let's just go. If you guys are not too tired, I'll just like to go a few slides and then take a break. Yeah, is everybody okay? Yeah, okay. So let's move on. So we look at this concept of an EPS bearer a little bit more. Okay. Remember, what does EPS stand for? Evolved Packet System. Yeah, good. So somebody knows all the acronyms, which is very good. EPS is essentially a connection-oriented network where the 2 points are the UE and the P gateway or PDN gateway. And this connection is called an EPS bearer. The connection between the UE and the P gateway is referred to as an EPS bearer. And on this bearer, we provide transport of packets with certain quality of service attributes. Now, what are these quality of service attributes? Well, we have four important ones. They are QCI, ARP, GBR. GBR stands for guaranteed bit rate. QCI stands for quality of class indicator. So we have about 9 quality of class indicators. We have ARP, which is an allocation and retention priority. Okay, it's not address resolution protocol, which you would have done in communication protocols. Okay, ARP stands for allocation and retention priority. And then GBR, which stands for guaranteed bit rate, and AMBR, which stands for aggregate maximum bit rate. So this was a diagram that I showed you earlier, which shows the different types of bearers that you can have. Okay, we have the EPS bearer is the bearer that goes between the UE and the packet gateway, and it's made up of radio bearers, S1 bearers, and S5, S8 bearers. Now, this quality of service, as I said, there are 9 possible quality of service class indicators in UE, in LTE, and these are numbered 1 to 9. Now, some of them have very small packet delay budgets. For example, if you have QCI class number 1, which is used for conversational voice, we have a budget of 100 millisecond end to end, okay, so which is not very large. And we also have a packet loss rate of 10 to the power minus 2 or 1 in 100. Okay, something like a video streaming, you have a smaller packet loss rate, 1 in 1,000, but it can have a larger delay. Okay, now this is all probably drawn up by some committee that sat down together and looked at that. Now, the thing that was really surprising to me was that they've allocated real-time gaming 50 millisecond budget delay. Okay, that means they're expecting people playing real-time gaming to have a better service than those who are having a voice conversation, because if 2 people are playing real-time gaming and their budget is 50 milliseconds, so their packets will, if there was a choke point, their packets will get through the network faster than those with voice. Okay, so we move on. So you can see that different types of services have different attributes. Now, how do you think you will use these attributes? Okay, so as I said earlier, we have 2 types of bearers. We have bearers that carry signaling and bearers that carry data. Now, another term that we'll talk about a little bit is the word context. Okay, so when we have an RRC connection, the E node B creates a context for the UE. Okay, and this is very similar to a PDP context very similar in concept, but not exactly the same. Okay, but in this particular case, associated with a context is a list of bearers, and in some of the early releases, they are saying that there's going to be 4 data radio bearers associated with each context, and each bearer will have some logical channel ID. Okay, and you know of this concept of having logical channel IDs. You would have done that in some of your other communication network subjects. It's something that's used for switching information as it goes through various pieces of equipment. Okay, and associated with a bearer is some information. Normally we give certain high priority for VoIP bearers. So it'll have information such as whether it's carrying VoIP or not, if there's HARQ being used, and what's the maximum bit rate, and so forth. Now, previously I told you about these 2 terms, default bearer and dedicated bearer. So what's the difference between these 2 terms? Well, the main difference is that in a default bearer can carry all kinds of traffic without any quality of service. Okay, so it doesn't prioritize traffic according to quality of service. So it's like a best effort. A default bearer is a best effort bearer. Okay, and this is the bearer that is initially created during the attach procedure. As soon as you attach to the network, you get allocated a default bearer. Now, for some communication, the default bearer may be good enough, but if you want a dedicated bearer, then you have to request for that, and you have to be allocated a dedicated bearer. So a dedicated bearer only carries a certain type of flow, for example VoIP. Okay, and it is established after the attach procedure, and on demand. Okay, so it's not automatically set up. Only on demand is a dedicated bearer set up. Okay, so this is a good question for you to know the difference between the terms dedicated bearer and default bearer in the context of LTE. Okay, so I think this will be a good point to take a short break. Section number 3 of lecture 5, which is on traffic operation. Okay, so we're going to see a little bit more details about how uplink and downlink data transmission is going to take place. Now, one of the important things to know is that we talked about channel quality indicator. Okay, all UEs are constantly taking measurements on those reference symbols and reporting these measurements on the uplink to the E node B, and the E node B collects all these measurements and it performs a scheduling function. So we have a scheduler in the E node B which determines how data should be transmitted on both on the downlink as well as on the uplink to the user equipment. And just as in the downlink, information is scheduling decisions are done by the scheduler, even for the uplink, all scheduling decisions are made by the E node B. Okay, so in order for the E node B to make the decision, well, at some stage the UE has to send a scheduling request saying, look, I've got data to transmit on the uplink, can you give me some resources? And when that information is received at the E node B, the E node B makes a scheduling decision and says, look, I'm going to allocate you these resource blocks, and that's all transmitted on the physical downlink common control channel, and that's the scheduling grant information, and then the data is sent on the uplink, on the physical uplink shared channel. Okay, so we're sending both control as well as data information on the uplink direction, and when the data arrives at the scheduler will check the data, and it will either send a positive or negative acknowledgement on the downlink channel. Okay, Now, how does the scheduler work? Well, the scheduler has to remember you're performing not only downlink scheduling decision, but you're also performing all uplink scheduling decisions. Okay, so it's a highly centralized form of scheduling. So what sort of information does it use? Well, it will use information such as the category of the user, and I'll explain what the category of the user is on the next slide. And you also have to see how many radio resource blocks are available for allocation, and what sort of measurements are we getting from the users, and what are the quality of service parameters that are being requested by this particular UE. So based on all this information, we make a scheduling decision. Okay. Now, in the scheduling process, there's two types of scheduling. There's something called static scheduling, semi-static scheduling, and dynamic scheduling. Okay. Now, there are some resources that need to be permanently allocated. Okay. So, for example, certain types of signaling channels have to be permanently allocated, and so we are sort of assigning certain resources for those. And then there are other that referred to as semi-static scheduling. So, for example, if you have VoIP traffic, you usually allocate resources for VoIP traffic in the semi-static scheduling. And once you've gone through this, you have an idea of how many resource blocks is needed. So this is an operation that is done every 20 milliseconds. Every 20 milliseconds, we determine how many resource blocks are going to be available for the remainder of the users. Okay, because we know how much is needed for static and semi-static purposes. And so then on a millisecond by millisecond, we perform the scheduling and we allocate the remainder of the resource blocks for the dynamic scheduling purposes. Okay. Now, in the I talked about UE category earlier. What does that mean? Well, there are different categories of UEs, and so you have UE category 1, 2, 3, 4. Okay. Now, each one of them has different. UE1 category 1 will be the cheapest one, and UE category 5 will be the most expensive one, meaning because it is expected to have 4 receive antennas, and it will be able to support up to 4 downlink MIMO streams. Okay, now these kind of handsets, as far as I know, these handsets are not yet available in the market, but UE category 1 and UE category 2 are already available in the market. Now, the other thing you will also note is that on the uplink, none of them, UE1 category 1 to 4 do not support 64 QAM. Only UE category number 5 supports 64 QAM. Okay, so that is really a high-end user equipment. So, as depending on the number of streams that it can support and depending on the number of receive antennas it can have, you can get higher and higher data rates. So it is expected with UE category 5, you can go up to 300 megabits per second with 4x4 MIMO and so forth. Okay, so how exactly, let's just go into a little bit more detail about data transmission in the downlink. Now, we know that all data link transmission in downlink is done on a channel called PDCCH. In this PDCCH, we allocate 2 resource blocks at a time. Okay, and that's called a PRB. Okay, a minimum of 2 resource blocks are allocated by the E-node Bs. Remember, a resource block, which you will remember from the test as well, a resource block is 12 subcarriers by 7 OFDMA symbols. Now, when we allocate resource block, the UE has no idea which resource blocks were allocated. Okay, so it cannot go searching every resource block to see if its data is there. So what we do is on the control channel PDCCH, we send information telling the user where its data is. Okay, so it tells on which resource blocks is your data and on which slots, and a slot meaning within a frame. Okay, and how are the data modulated? Which modulation schemes are you using? Because you need all these three pieces of information to be able to find your data which is transmitted on the downlink. Okay, so we have the PDCCH, and once you look at the PDCCH, you will know which resource blocks contain your data. Okay, so and then once you know the resource blocks, you can go and get your data from there, and you know which modulation schemes it's being used, so you can demodulate and do all of the necessary processes to extract your original data. So this PDCCH, where is it transmitted? Well, because it contains all the information about how all the resource blocks are allocated within a subframe, it has to be sent right at the beginning of a subframe. So the PDCCH occupies one. You only have one PDCCH per subframe, but it has to come right at the beginning. Okay, because it helps to retrieve the transport blocks from the shared channel. Okay, now you can see on the diagram that I gave you earlier, the sheet that I photocopied from the textbook and I gave you earlier, you can see that the PDCH are these red blocks here. Okay, so here we have again, on all the subcarriers, on all the resource blocks, we transmit PDCCH right at the beginning. Okay, so here we have 2 symbols with PDCH, here we have 3 symbols, here we have 2, and here. So it can vary the number of. So obviously, if all your resource blocks are fully utilized, you may have to use 3 of them. Sometimes, if you're not using all your resource blocks, you might the information that you need to send in the PDCCH might only fill 2 slots and so forth. Okay. Okay, now a couple of things about PDCCH. Without reading the PDCCH, you can't decode the rest of the data. And again, as I mentioned a few minutes ago, its size and locations are not predefined, since the amount of control data depends on the traffic. Okay, if you have large amounts of traffic, you will need more PDCCH. One of the things that forms part of the PDCCH is something called PCFICH, okay, Physical Control Format Indication Channel. And this channel allows a UE to decode the PDCH. Okay, so these bits are in fixed positions, and they allow the UE to decode the PDCCH. Okay, now how does it work in the uplink? So we talked about the downlink. In the uplink, again, a UE has no dedicated resources when it wants to transmit data. When new data arrives at the UE, it has no dedicated resource. So it has to request for resources before it can transmit. So, for example, you do a HTTP on your LTE handset. The question goes out to the eNode B saying, "Look, I've got packets to send. Can you give me some resources?" So the eNode B looks at the request, and based on available resources, it'll grant resources to the UE. And the UE starts its data transmission, and as it starts its data transmission, it also reports the buffer status. How much data do I have in my buffer? Okay, because if you have a lot of data in your buffer, then you may have to be given more resources. Okay, and this is how the uplink, and all of this takes place on the physical uplink common control channel. Okay. Now here's a diagram that shows the uplink channel. Okay, now because of time constraints, I'm going to let you figure this out. I'm not going to cover every slide in this subject. There are some bits that I'm going to let you sort it out, because otherwise it'll be too much of me talking and too little of you doing any work. So I'm going to leave you to figure that one out for yourself. Now, in the PDCCH, you also have something called downlink control information, or DCI, to indicate resource assignment in uplink or downlink. Okay, and this could be for a number of different purposes. One of the things that we do in LTE is that on the downlink we perform link adaptation, but on the uplink we do power control. So in order to get power control messages, we use the DCI to transmit that information, and also the resource block assignments. Okay, which resource blocks are going to be used for the UE to transmit on uplink, okay, and that's sent on the DCI. And as far as the data transmission, it does it on the PUSCH, which stands for, okay, I'm going to move on. Okay, the next thing is about measurements. Okay, remember, every UE has to take measurements and report them, because without the measurements, why do we need the measurements? We need measurements for scheduling, because no measurements, no scheduling, no packet transmission, no communication. Okay, so UE reports its measurements to the E node B, and these measurements are used for link adaptation, okay, to determine what modulation and coding scheme should be used for the downlink transmission. It's used for mobility related issues. Okay, so you're saying, what is my, we saw earlier, we not only report our serving cell signal strength, but we also report our neighbor signal strength, because when we have to do a handover, then also interact mobility. If the UE is leaving the coverage area of an LTE, okay, it's got to start reporting measurements not only of LTE networks, but also of UMTS or GSM networks that it can see. And remember, in that, I didn't go into the detail, but if you look in the SIB, the SIB contains parameters related to nearby neighboring UMTS cells and also neighboring GSM cells. So you can take measurements on those at the time when you're moving out of one RAT. RAT stands for radio access technology. Okay, so when you're moving from one RAT to another RAT, okay, you have to send those measurements. So the UE measures the serving cell, the neighbors, UMTS cells, GSM GPRS cells, and if there's a CDMA 2000 network, then it will be also measuring CDMA 2000 measurements. How does it make the measurements? Okay, I showed this idea. I told you about the reference signals. Remember, in that diagram there were the dark dots there. Those represents reference signals, and those reference signals is where measurements are taken. Okay, now the other thing is, it's very expensive to send the entire signal to noise ratio. If, for example, you have signal to noise ratios that vary from from minus 100 dBm to about minus 10 dBm, which is a very large range, it's very difficult to send numbers in that range. So what we do is we have sort of represented the channel quality in terms of a channel quality index. So there is one of 16 numbers that we can send. Okay, so if the UE sends a number between 0 and 15, so it only needs 4 bits effectively to send this information, and each of those bit pattern corresponds to one of these CQI index, and it sort of identifies what is the modulation scheme that should be used at the transmitter and what is the coding rate that should be used. So based on the CQI, the transmitter can then adjust the modulation scheme as well as the coding scheme that's used. Okay, so these measurements are reported by the UE. Apart from CQI, remember when we talked about MIMO, we said we have the rank indicator and also the pre-coding matrix indicator. Two other information that needs to be sent when we have a MIMO system operating, because that's needed for MIMO operation.
Closed loop.
Yeah, closed loop. Another aspect that we have in LTE radio transmission is HARQ, hybrid automatic request. What happens here is that in HARQ is that when we have data blocks that are received in error, they need to be retransmitted. Okay, so HARQ is a process which facilitates that. So HARQ runs in both the UE as well as in the eNode B. So in the eNode B, for example, if the eNode B was to send a packet on the downlink and the UE was to assess that packet and say, I've received this in error, how does it know? It just does a CRC check, cyclic redundancy check, on the data that was received, and if the CRC check is different to the CRC that it was received, then it knows that there's an error associated with the packet. So it sends a negative acknowledgement, and when it gets a negative acknowledgement, there's a retransmit. Okay, now usually these retransmits get a higher priority over the standard packet transmission. Okay, why? Because of the delay deadlines. Okay, remember we talked about those 100 millisecond delay deadline, 300 millisecond delay deadline, and so forth. So obviously, packets that have been transmitted, that have been waiting in the buffer long, have been transmitted, received in error, you want to retransmit them back as quickly as possible. So what the receiver does is it combines the previously corrected packet, previously received packet which is incorrect, and the new packet, and it combines it together through a process called soft combining, and it comes up with a better packet which may satisfy the test, and it will send the acknowledgement. Okay, a little bit more detail. You initially send the PDCCH identifying where the data is coming, then you send the data on the PDSCH. The UE puts the data in the soft buffer, and then it says this is in error. So what does it do? It sends a negative acknowledgement again on the control channel, on the physical uplink common control channel, and what the UE does is it does a retransmission of the transport block, and this time it combines the two transport blocks in the soft buffer, and if it's able to successfully combine these two transport blocks, then it sends an acknowledgement, and that's the basic idea behind ARC. And the same thing happens in the uplink direction as well. Okay, so that's a quick overview of lecture 5. Okay, thanks.